Hi folks, today we're going to do an experiment to measure the specific heat capacity, sometimes called specific thermal capacity, of various different metals. Now what we mean by that is, here for example is three materials. We've got a kilogram of steel, a kilogram of aluminium, a kilogram of copper. So the specific heat capacity is how much energy it takes to heat a kilogram of that material by 1 degree. So how much energy it will take to heat this by 1 degree, how much will it take to heat that? Now you may think that if you supply the same amount of energy, let's say 1,000 joules to this and 1,000 joules to that, they would go up by the same temperature, being as they're the same mass. And that's what we're going to look at. Is it the same? Can we measure how much? Is there any differences? Are there big, small differences, whatever? So, to heat these up, we're going to use immersion heaters. These are little called immersion heaters. They fit inside quite nicely inside each one. And you connect that to the power supply, measure the current and the voltage, turn it on, and it starts to heat up. And we can measure the current, measure the voltage, and measure the temperature. You'll notice there's a small hole in each one. That's so that we can put a thermometer in there to measure the temperature. We're going to use a data logging thermometer on the computer. But we can measure the temperature as it goes up. And so we can work out how much temperature goes up for how much energy is supplied. Now here's the circuit. Here's your power supply. Current goes round here, into that heater there, into the copper block. It then comes round through the ammeter in the middle, then round into the aluminium block, and then back round again. So you've got a series circuit. So we know in a series circuit the current is the same value at every point in the circuit. So we've got one ammeter, and that's measuring the current going around the entire circuit. That's constant for both devices. Now to measure the energy supplied, we're going to use this equation, which is one you're actually given for GCSE. The energy supplied is the current, which we're measuring here, times the voltage, times the time the circuit's running for. Now, here's a voltmeter and here's a voltmeter, 2 voltmeters. Well, you may think, as it's series, these two heaters are the same, the voltage should be the same for each one. Well, it would be if they were perfect, the same resistance, but we're not sure, so we'll put a voltmeter on and get the actual value as close as we can. So we have a voltmeter measuring the voltage across this heater, a voltmeter measuring the voltage across this heater, and we'll have a stopwatch to measure the time we're heating for, with your thermometers, in our case data logging temperature sensors, measuring the temperature, and then we can see how much energy is supplied, calculate that using this equation. We can see what the temperature rise is, see if there's a difference, and do some calculation. So that's what we're going to do. So the actual setup is over here. Let's go. Okay folks, here we are. Here we can see the setup as I do it on the board in front of us. Let's recognise the components. We have the power supply here, supplying a current through the cable to the first heater unit there in the copper, goes through the ammeter here into the second heater block, which is there, and then back to a power supply. So that's your series circuit. We have a voltmeter here measuring the voltage across that heater, a voltmeter here measuring the voltage across that heater there. So we have the 1 ammeter reading, 2 voltmeter readings. Here's your timer for how long the circuit's been on, so we'll click that. There's the power supply, and we're all ready to go. There's the initial temperatures. Let's have a little look. One of them's a bit hotter than the other to start with because I was playing around the circuit earlier. But as we haven't started yet, that's not the actual temperature. I'll record those in a moment. So we're all ready to go, apart from I'm going to insulate these blocks first. We can see a lot of heat would come out of these into the air, so let's try and reduce the heat loss, which we'll do by covering them in a bit of cloth or bubble wrap. I'll get that done and then I'll come back to you. Okay, as you can now see, suitably wrapped in bubble wrap to reduce any heat losses. Heat-proof mat underneath to stop the bench burning in case it gets too hot, although I don't want to go that hot. So everything's ready to go. So I've started the temperature recording, I'm just about to start that from fresh, sorry. So there's stop, let's start the temperatures. Do you want it to save it? No. So we've got the starting temperatures, doesn't matter we haven't started the experiment yet, of 22.5 and 23.8. I'll write that down in a moment. 22.5 and 23.8. And then the voltmeters and ammeters and the timer ready to go on now. So here's the timer. Start, everything's running. The clock's running. There is the ammeter recording about 3.3. Now you'll see this jumping around a bit. It does do, but it doesn't move much from 3.3. And once it's warmed up and got initiated, it stays much more constant. So I'll record what that stays at throughout the experiment. That one for the copper is about 10.2. 10.2, yeah, it's around about 10.2. It's moving around there. The voltmeter on the aluminium, as you can see, is a bit higher. That's why we've got two voltmeters, because they're not identical. 10.8. So the experiment's kicking off, and the temperature will start to rise in a short while. We've already got a slight rise in temperature there. So I'm going to record all the data in a very rough table, not as of a higher quality as I'd expect you to do in your books. So here's my table. I've got the aluminium, the mass, the start temperature, which I'll put in a minute, the start temperature, the end temperature, time, the current, and the voltage across each one. So I'll be getting on with that experiment. This is going to take 10 minutes or so. So we could sit here for 10 minutes, all just looking at these wonderful meters changing, but I think that might be a bit boring. Well, this is getting exciting now, isn't it? Look at this. Temperature of the copper, 49.1. Temperature of the aluminium, 34. So, really exciting stuff. Don't us physicists have an exciting life? Anyway, let's do a little bit hotter. Hi folks, well things are really hotting up. See what I did there? As we can see, if you look at these temperatures, actually you can see from there, the aluminium block is only 36 degrees, but the copper is up to 53.1, 53.5, it's shooting up. The voltage about 10.7, about the same, 3.25, that stayed up pretty consistently. We've done 7.5 minutes now. It's so exciting, isn't it? Okay, well, us physicists like things like this. Now, key point is how long we're going to carry on heating for. I think we've got enough data really with the copper up to 55, that's sort of approaching a 40-degree increase in temperature. It's about 35 now. The aluminium's gone up quite a bit as well. So I think we've got nearly enough data. So I'm going to turn off, I think when the copper gets to about 60, that will be a time of coming up towards about 10 minutes. And I think towards 10 minutes we'll probably do. So, I'll get myself ready to turn things off. Okie dokie, so, copper, 58, about 60. Now when I do turn it off, we don't have to record the temperature there and then, because the heat's been going in, will still keep flowing out towards the thermometer. So it will be carry on for quite a bit. I'll get my pen ready to write some wonderful details down. Okay. The copper's now at 60, the time's approaching 9 minutes, so I'll turn it off on 9 minutes, and here we go, 5 seconds, 4, 3, 2, 1. Okay, time 9.00 minutes. So look at the temperatures, you'll probably see, if I move it over here, that the temperatures are still going up. And what we have to do is record the maximum temperature. So, there's no more heat going in, but it's the heat we've already supplied, we've already paid for, so to speak, going into these blocks, and we need to record the actual peak they reach. Still going up. So as you can see, they've been turned off now for about a minute, they're still going up. 65.5, 0.7. Obviously they're both still going up. As you can see from the meters, there's no more heat going in. 66, will it go up any more? 66, yeah, still going up, still going up. So the immersion heater, of course, at the centre of the block was very hot and the heat was spreading out by conduction. Remember all that from the fourth year? The conduction was spreading out, the heat out. Ooh, is it reaching the maximum? I don't think that's going to go up anymore. So 42.9 seems about top, 68.1. Yeah, and that is quite a while after we turned the heater off. So you can see the inherent heat spreading out, equalising around the block, so we get a fair old result. And of course, because we insulated and we're not losing too much heat, it's sort of sharing itself among the metal, which is a good conductor. So there's our final temperatures. Oh, is that one more? 43 and 68.2, is that then? 43.0, 68.2, oh, 68.1. Yeah, that's definitely it. Okay, folks, so there's our data. So what we need to do now is complete our table and do some calculations. Okay, back in a little while. Okay, so here's my data. Now, it's not a very good table. In fact, it's not a table at all. It's rough. I just wrote it down as and when. But we can see we've got all the information we need. The aluminium, the mass. We've got the start temperature, the final temperature, the start temperature, final temperature for two different metals. The time, 9 minutes, 9.00 minutes it was on the clock. We need that in seconds though. In seconds is, question mark that says. We've got the current, which averaged around about 3.25. It didn't vary too much from there. Now these 2 voltmeters here were fluctuating a bit as you saw, so I'm not putting the 100th of a volt in, but they were pretty well averaged at about 10.7, 10.5 for the other one, which is okay, so we're 3 sig figs, we can do that. So you can calculate the temperature rise in aluminium, the temperature rise in copper, obviously the difference between these values. So then we know the temperature rise, and we've got the data to calculate the energy supplied to each one, and then the specific heat capacity. So what you need to do now is pause the video and record that data neatly in your books, please, folks. Right, we can now calculate specific heat capacity using the data we've already got. So here's the equation for specific heat capacity. It's got symbol C, and you should know this equation. Delta Q, which is the energy supplied, that's what we just calculated with our experiment for each material, equals the mass of a block, and both of ours were 1.004 kilograms, times specific heat capacity, that's what we're trying to find out, times the temperature rise. Now we recorded the temperature rise, we recorded the mass, we've calculated the energy supplied, so we can work out the specific heat capacity, which remember is how many joules of energy do you need to raise the temperature of 1 kilogram of that material by 1 degrees C. Now, algebra time, you rearrange this to get C, which is what we want. So C, we move the M onto this side, move the delta T onto this side, and we get C equals delta Q over M times delta T. Don't worry about the delta symbol if you don't know it. It just means changing. It's physicists don't like writing, so it just means changing. So that's change in energy supply, the difference between what you had before and what you had after. Change in temperature, it just makes sense. Don't worry about it. So we've got specific heat capacity equals the energy supplied divided by the mass times the temperature rise. Make sure you do those two first. So there you go. You can now calculate the specific heat capacity of aluminium and specific heat capacity of copper, and if you look on the internet accepted values for those, we can see how close we were with this experiment. Okay, were we close?